Hi everyone, my name is Ashley Watts and I'm recording this video for the UNE Online Biochemistry Unit 4 case connections. So the first case that I chose to do was case 1, and it reads, a newborn girl appeared normal at birth, but within 24 hours she developed lethargy, hypothermia, and apnea. The attending physician suspects a metabolic disorder and orders a panel of labs. And the question we are supposed to answer here says, which diagnostic would be best to distinguish between a urea cycle disorder and a disorder in beta oxidation. And our options are blood glucose, urinary acids, serum fatty acids, and plasma glutamine. So starting with blood glucose, so given what we know already about beta oxidation deficiencies and urea cycle disorders, I don't really think that blood glucose would be the best because between beta oxidation and urea cycle, they don't really have much of a role in affecting like blood glucose in general. So I don't think that that one would really be the best. Urinary acids, I said this could be a potential option because, you know, in urea cycle disorders, we would expect to see a high level of urinary acids and increased blood ammonia, which is due to, you know, the accumulation of ammonia in the blood. And I think that although this is one of the main options, I found it interesting from doing research on this topic that there is research that says that although like many people do use this method, it is more of a specific means of differentiation between like different levels in the urea cycle to determine like where there's the deficiency. So instead of like looking at the urea cycle as a whole and saying, yes, it's deficient, it's more going to show you what level in the urea cycle that alteration is. So then there's serum fatty acids, and I said this is also going to be a very good diagnostic between a urea cycle disorder and a deficiency in beta oxidation. And so I said in a patient that has a disorder in beta oxidation, we would expect to see high levels of free fatty acids. This is going to be because you are unable to transport those free fatty acids into the mitochondria using that palmitoyl transferase 1 transport enzyme. And so this would also allow you to say, like, you know, if the levels are high, oh, look, it's a disorder in beta oxidation, where if it's low, you can kind of differentiate between urea cycle disorder and beta oxidation. So we know that the urea cycle is an anabolic process and it requires ATP. And for blood sugar, we know that during the fasted state, ATP will come from the oxidation of dietary substrates, things that we eat. And in the fasted state, you know, our energy is going to come from beta oxidation that occurs in the liver. So that's kind of interesting to think about too, if you put that all together, what you would expect to see on a panel of labs. And next we have the plasma glutamine levels. So, you know, I really don't think that this would be the best just because it's too nonspecific for determining between beta oxidation disorder and urea cycle disorder. So I really don't think that would be the best means. So, you know, with that being said, like I've mentioned, again, I think that you could use urinary acids or the serum fatty acids to really help you determine between beta oxidation or urea cycle disorder. So the next we are given the panel of labs. So it says a full blood workup was ordered for this female and the data is presented below. The initial blood ammonia level was elevated at 314 and we could see the normal range is between 17 to 80 and it rapidly increased to 600. And the urine orotic acid level was elevated as well at 473, which the normal levels are between 0 and 3. And the plasma citrulline level was also normal. A little bit under normal, but still within the normal limits. And the question is, in this patient where orotic acid levels are elevated, list one urea cycle enzyme is most likely deficient and one that is most likely to be impaired. So I said the most likely deficient enzyme will be ornithine transcarbamylase, or also known as OTC, and the carbamyl phosphate synthetase 1, it's a mouthful, is least likely to be affected. And I said this is because CPS1, it appears upstream of the carbamyl phosphate in the urea cycle pathway. and we would expect that it would be active and normal. So just a little bit of a background quickly. We know the urea cycle is an essential process. It's required for the disposal of nitrogen from catabolic processes. And when there's a dysfunction in the urea cycle in general, we're going to see an accumulation of ammonia. And this is also pretty much the accumulation of ammonia is what's referred to as hyperammonemia. And we know that this patient is found to have significantly elevated ammonia, elevated urine orotic acids, and normal plasma citrulline levels. So typically in patients with OTC deficiencies, we're going to see this consistency in the labs. It's an X-linked recessive disorder. And so in females, although it is more rare than in males, we are going to see that lethargy and that apnea, which we see perfectly demonstrated in this patient, given the prompt. So high urine orotate is suggestive of an increase in production or accumulation of the carbamyl, am I saying that right? Phosphate. So it's not in an OTC deficiency, the body is not using the pool of ornithine carbamyl transferase to synthesize citrulline. So we're going to see that accumulation of carbamyl phosphate in the mitochondria, and it's going to slowly leak into the cytoplasm and become redirected to pyrimidine synthesis. So it's going to be used for something else. The increase in urine orotic acid will lead to the orotic aciduria, which we have learned from the lectures. This is because the orotic acid isn't able to be properly used, and that's the only way that we can properly eliminate all of that accumulation. So it's just going to go out through the urine. So that's that one. And the next one is a 4-day-old infant. Patient A is being followed in your clinic. Her birth weight was 5.9 pounds in her pregnancy, and the pregnancy and birth was vaginally, were normal. Results of the newborn screening demonstrated phenylalanine, PHE, level of 6.6, which is severely elevated. A presumptive diagnosis of phenylketonuria was made and additional samples were obtained. The parents deny any family history of PKU. First question is, as a consequence of this presentation, which amino acid may become essential? So I said, as we can see, and like we've learned in lecture, the patient has a markedly elevated phenylalanine level, which is indicative of PKU or phenylketonuria. We know that phenylalanine is derived from the dietary intake, and it's found in a lot of different artificial sweeteners, as well as with recycling of endogenous amino acids. So, in a patient like this with phenylketonuria, it's due to the impairment of phenylalanine. So we're going to see that the next thing that's going to become essential is tyrosine. So it becomes conditionally an essential amino acid and has to be supplied from an exogenous source, just like we learned in lecture. The next bullet point we see in question is phenylalanine dietary restriction was initiated at 14 days of age with good response of plasma phenylalanine levels that dropped to the normal range. Question is, what are the potential causes of a presentation of phenylketonuria? So I did a lot of research on this dietary aspect of phenylketonuria because I thought it was pretty interesting. So I found that a lot of patients with PKU have to be very conscious of their diet, and although it does occur at a young age, it's the parents being aware of the diet. So there's a lot of research that shows avoiding artificial sweeteners such as aspartame and following a low protein diet is an essential part of good progression in patients with PKU. And this is because artificial sweeteners like aspartame can't be broken down by phenylalanine. And so if this regimen is not followed, phenylalanine and the other metabolites will build up, and it can lead to significant brain damage. And aside from brain damage, it can also lead to, long-term deficits like mental retardation. So I thought that was pretty interesting. And next, I'm just going to talk a little bit about some causes. So we know that, like I said, doing a lot of research on this and knowing what we learned in lecture, PKU is an autosomal recessive metabolic disorder caused by a mutation in the PAH gene. So being autosomal recessive, it makes sense since we know that it says that the patient's parents deny any known family history of PKU. So that's why we see, it makes more sense that the patient has it since we know it's recessive and her parents don't have any known history of it. So when properly functioning, we're going to see that hydroxylation by PAH with B4, the cofactor, in the presence of oxygen. We're going to see the formation of phenylalanine to tyrosine. So in addition to phenylalanine hydroxylase, BH4 is a cofactor, as we know, that's required for the conversion of phenylalanine to tyrosine. We can also see a deficiency in BH4 also leads to patients presenting with PKU because that conversion, like I said, is still not able to take place. And phenylalanine being unable to be metabolized by the body is why we see lead to brain damage and, like I said, mental retardation. So that's why the importance of being on that dietary restriction therapy is so important. So we see the final question, we see a graph, and it says another patient, patient B, is being evaluated for suspected PKU. BH4 loading tests are performed on the patients and presented as below. And we see that the tablets of synthetic cofactor, B4, dissolved in 20 milliliters of water in a dim light and administered to the patients at least 30 minutes before a meal. Blood tests were drawn at hours 4 and 8, and we see that. So when we look at the graph, first of all, we see that the level of phenylalanine is actually increased after loading in patient A, whereas in patient B, we see a decrease in the phenylalanine levels after being administered BH4. So I said that given what we found in the graph, we can assume that the patient A has a deficiency in the PAH or phenylalanine hydroxylase deficiency, and patient B most likely has a BH4 deficiency since we see after being administered BH4, the levels of phenylalanine drop. So we're seeing that conversion, whereas we're not in patient A. And I did some research, and I found that research actually supports this, stating that, for example, there's been many different research studies that show after oral BH4 challenging in patients with PAH mutations, they are often found to have an increase in the presence of BH4, which we know is a chaperone to PAH, meaning it protects it from the misfolding during synthesis. So yeah, I thought that was very interesting, and it supports this summarization of tests very well. So yeah, thank you so much, and I hope you enjoyed this.